Hey everyone, and welcome to the Deep Dive.
It's great to be here.
Today we're diving deep into the world of single-phase microinverters.
Those little powerhouses behind solar panels.
Exactly right.
Yeah.
We all know about those big, bulky inverters.
Right, the central inverters.
But microinverters, they're like giving each panel
its own brain.
Yeah, its own personal power converter.
Yeah.
So why is that such a big deal?
We think about what happens when one panel gets shaded.
Uh-oh.
In a traditional system, the whole thing kind of...
The whole thing suffers.
Yeah, the whole string.
Yeah.
But with microinverters, each panel's like, I'm good. I'm going to keep producing power.
Yeah, they're independent.
Exactly.
I love that.
Yeah.
It's all about maximizing efficiency.
Absolutely. Especially in, real-world scenarios.
Real world, yeah.
Where you've got, maybe some trees or a chimney casting shadow.
It's not a perfect world out there.
Oh, it's not.
But designing these things, these little microinverters,
Oh, yeah.
sounds like a real engineering challenge.
It is. It is.
One of the first things I think about is voltage boosting.
Right.
A single solar panel, it doesn't produce that much voltage.
It's low DC voltage, yeah.
But you need a lot of voltage to connect to the grid.
Exactly. So how do you get there?
Yeah, how do you do that?
Well, you got to boost it, and there are different topologies, different ways to do that.
Okay.
You've got like flyback converters,
Okay.
which are simple, but they can be a little bit hard on the switches.
Oh, what does that mean?
It means they might wear out a little faster.
Oh, okay, so that affects the lifespan.
It can, yeah.
Right.
Then you've got boost converters, which are super efficient.
Okay.
But they might need bigger inductors, so the microinverter gets a little bulkier.
So it's a trade-off.
Always trade-offs.
Side versus efficiency.
Exactly. And then there's the CLL resonant converter.
Okay.
Now, this one's interesting. It offers a wide range for something called zero voltage switching.
I'm intrigued. Tell me more.
So this basically means it's really efficient, less energy loss as heat.
Okay, that sounds good.
But it needs a more complex control system to make it work.
So more complicated, more extensive.
Potentially, yeah.
It seems like there are always these trade-offs.
That's engineering for you.
I'm sensing a theme here.
Yeah, there's no free lunch.
So what are some of the trends in the field? What are people excited about?
Well, one big one is going transformerless.
Transformerless, what does that even mean?
It means getting rid of the transformer.
Okay, and why would you want to do that?
Well, it makes the microinverter safer,
Okay.
more efficient, and smaller.
Oh, so like three birds, one stone.
Exactly.
I like it.
But there's a challenge.
There's always a challenge.
There is. It's leakage currents.
Leakage currents. Okay, that sounds a little scary.
It can be. It's basically unwanted electrical paths to the ground.
So like energy escaping.
Yeah. Think of it like a leaky faucet. You're losing valuable drop.
Oh, I hate a leaky faucet.
Nobody likes those.
So how do they fix that?
Well, they're working on things like direct connection paths
Okay.
to kind of plug those leaks.
Got it.
And there are some new topologies that try to tackle these issues head on.
Oh, really?
Yeah. For example, there's this paper I was reading called A Novel Single-Phase Grid-Connected Transformerless Solar Microinverter Topology with Power Decoupling Capability.
Wow, that's a mouthful.
Yeah, it's a long one.
Okay, so what's so special about this topology?
Well, it claims to provide power decoupling without needing extra components.
Okay, hold on. Power decoupling.
Yeah. You know how your solar panel produces power, but it's not always smooth.
Kind of like up and down.
Yeah, like a choppy sea.
I get it.
You need to smooth that out before you send it to the grid.
Okay, smooth it out so it's nice and consistent.
Exactly. That's what power decoupling does.
So it's like a shock absorber for the electricity.
Perfect analogy.
I like that.
Traditionally, they've used big electrolytic capacitors.
Okay.
But those things are bulky. They don't last forever.
Right.
And they can be a bit unreliable.
So this new topology is trying to ditch those capacitors.
Exactly. It's all about finding more elegant solutions.
So more efficient and smaller.
That's the goal.
It seems like there's so much innovation happening in this field.
Oh, yeah. It's a really exciting time.
But, before we get too far ahead,
Sure.
you mentioned modulation techniques earlier, and I feel like we need to unpack that a little.
Absolutely. It's a crucial part of how these microinverters actually function.
Right. So what are we talking about here?
Well, it's all about how the microinverter regulates the power flow and synchronizes with the grid.
Okay.
You're basically controlling the alternating current waveform.
Or waveform, right. Okay.
So you've got different techniques like sine, PWM,
Okay.
dual phase shift.
DPS.
Yep, and variable frequency modulation.
So many options.
Lots of choices, each with pros and cons.
Lay it on me. Break it down.
All right, so sine PWM, it's kind of the class S approach.
Old faithful.
Yeah, pretty simple, but it can lead to higher switching losses.
Meaning?
Meaning you lose some energy as heat.
So less efficient.
Right, then there's dual phase shifter, DPS.
Okay.
This one's cool. It uses soft switching.
Soft switching, what's that?
It basically makes the transitions between on and off states smoother.
Okay. Less jarring.
Yeah, which reduces losses.
So more efficient.
Exactly, but the downside is it can be a bit computationally heavy for the control system.
Ah, so more complex, more expensive, potentially.
It's a possibility, yeah.
Okay, and what about variable frequency modulation?
That one minimizes something called reactive power.
Reactive power. Now, that's a new one.
Yeah, it's basically power that doesn't really do useful work.
Like overhead?
Exactly, but it can make it trickier to achieve zero voltage switching.
Which we know is good for efficiency.
Right.
So again, trade-offs.
Always trade-offs.
Like a constant balancing act.
It is. You're trying to optimize for so many different factors at once.
Right, and on top of all that, they need to design control schemes for MPPT.
Maximum power point tracking.
MPPT, I've heard that term thrown around, but
Yeah, it can be a bit jargony.
yeah, what does it actually mean?
Imagine you're trying to fill a bucket from a hose.
Okay,
You want to find the spot where the water pressure and flow rate are just right.
to fill it up as fast as possible.
Exactly. That's what MPPT does for solar panels.
It finds the sweet spot.
Yep, the optimal operating point to get the most power out of the panel.
So it's like fine-tuning the panel.
Exactly, but here's the thing. Solar panel output can change throughout the day.
Right, the sun moves clouds, things like that.
Exactly, so the control system needs to be really fast and responsive.
To keep up with those changes.
Yep, it's constantly adjusting to make sure you're always getting the maximum power.
Like a tiny little brain working behind the scenes.
That's a great way to put it.
So we've talked about feeding power into the grid,
Right.
but are microinverters only good for that?
That's a good question, and the answer is no.
Well, there's more.
There's more.
We love it.
Modern microinverters are getting really sophisticated.
Okay.
Some of them have something called multi-port functionality.
Multi-port functionality sounds fancy. What is that?
It basically means they can do more than just feed power into the grid.
Okay.
They can also supply DC loads directly,
Like what?
like maybe some DC appliances or lights.
Okay.
They can charge batteries,
Ooh.
and they can even interact with energy storage systems.
Wow, so they're like mini power hubs.
Exactly.
That's incredible.
And then there's islanding operation.
Islanding operate. I love that term.
Yeah, it's a good one.
What is that?
Imagine the power goes out,
Uh-oh.
but your lights stay on.
How?
Because your solar panels with their microinverter have formed their own little grid.
Whoa, like an island of power.
Exactly.
That's so cool.
It's all about resilience.
Right, so you're not completely in the dark when the grid goes down.
Exactly. You can keep those essential appliances running.
So these little microinverters are getting smarter and more versatile all the time.
Oh, yeah, the innovation is amazing.
But before we get too carried away,
Sure.
let's talk about reliability and efficiency optimization.
Absolutely. Those are key factors.
I mean, it's great to have all these fancy features,
Right.
but what good are they if the thing breaks down after a year?
Yeah, reliability is crucial.
So how do they make sure these microinverters can handle the real world?
Well, it starts with minimizing power losses.
Okay, why is that so important?
A couple of reasons. For one, it makes the microinverter more efficient.
Right, less energy wasted?
Exactly. And secondly, it reduces heat generation.
Ah, so it runs a cooler.
Exactly, which means it's more reliable and lasts longer.
So it's a win-win. I
Exactly.
like those.
We all do.
So how do they minimize those power losses?
Well, one technique is called soft switching.
Soft switching, you mentioned that earlier.
Yeah, remember ZVS and VCS?
Right, zero voltage switching and zero current switching.
Exactly, those are both soft switching techniques.
Okay, and what do they do?
They basically make the transitions between on and off states smoother.
Like a general on and off.
Yeah, exactly. Less jarring, less energy lost.
So clever.
It's all about finesse.
What else do they do to boost efficiency?
Well, they also carefully select the semiconductor devices.
What are those?
Those are the MOSFETs and diodes, the things that actually do the switching.
Okay.
They use ones with very low resistance and really fast switching speeds.
So like a superhighway for the electricity.
Exactly.
Nice.
And of course, the design of the inductors and capacitors is important too.
Those are the passive components, right?
Yep, they all need to be carefully optimized to minimize losses.
So it's like an orchestra. Everything has to be in tune.
That's a great way to put it.
But there's another important aspect we haven't touched on yet.
Okay, what's that?
Electrothermal modeling.
Oh, yes.
What is that all about?
Well, it's basically a way to simulate how temperature affects the components inside the microinverter.
Okay.
By modeling the heat flow and the electrical behavior, they can identify potential hotspots.
So they can see where it might get too hot.
Exactly. And then they can optimize the cooling mechanisms.
To make sure it doesn't overheat.
Exactly. It's like a virtual stress test.
A sauna for the microinverter?
Yeah, something like that.
Making sure it can handle the heat.
Exactly, because remember, these things are out there on rooftops baking in the sun.
They need to be tough.
They do.
This is fascinating stuff.
It is.
But I'm also curious about those electrolytic capacitors.
The big bulky ones.
Yeah, you mentioned they have a limited lifespan.
Right, they're not the most reliable.
So are there any alternatives on the horizon?
People are working on it.
Okay.
There's research into things like film capacitors and ceramic capacitors.
Okay, and what's the advantage of those?
Well, they're potentially more robust and longer lasting.
So less likely to fail.
Exactly. The quest is on for the perfect capacitor, small, efficient, and built to last.
A worthy quest indeed. It seems like reliability is a never-ending pursuit.
It is. You're always trying to push the limits.
So are there any breakthroughs in reliability that have caught your eye?
One exciting area is the use of wide bandgap semiconductor devices.
Wide bandgap? Okay, now I'm really intrigued.
Yeah, it's pretty cool.
Tell me more.
So these are materials like silicon carbide or gallium nitride,
Okay.
and they offer much better performance than traditional silicon devices.
Like what kind of performance?
Higher efficiency, higher power density.
So they can handle more power in a smaller package.
Exactly.
That's incredible.
And remember, higher efficiency means lower operating temperatures.
Right, so even more reliability.
It all comes together.
It does.
It seems like the future of microinverters is incredibly bright.
It is.
All these new materials, new technologies coming into play.
And it's not just the hardware. There's also a lot of progress on the software side.
Okay, like what?
New control algorithms, more sophisticated MPPT techniques.
So it's a constant evolution on both fronts.
Like a technological tango.
I like that.
It's like a technological arms race to create the ultimate microinverter.
It is, in a way, but it's a race to the top.
Right, a race towards a more sustainable future.
Exactly.
This has been an incredible journey so far.
Yeah.
Delving into the intricate world of microinverters.
It's amazing how much technology is packed into those little devices.
It really is, but I feel like we've only just scratched the surface.
There's still so much more to explore.
There is one thing I wanted to circle back to.
Okay.
You mentioned active power decoupling circuits, or APDCs.
Yes, those are interesting.
Okay, so what are those all about?
Remember how we talked about smoothing out the power fluctuations from the solar panel?
Right, making it nice and steady for the grid.
Exactly. Well, APDCs take that to the next level.
Okay, how so?
They actively regulate the power flow.
Actively? Okay, so it's not just passive smoothing.
Right. It's more dynamic, more precise.
Interesting. So what's the advantage of that?
Well, for one, it can reduce the need for those bulky electrolytic capacitors.
The ones we're trying to get rid of.
Exactly. So that means smaller, more reliable microinverters.
Okay, I like that.
But the real game changer is that they enable more sophisticated grid interaction capabilities.
Okay, now you're talking my language. Tell me more.
Things like reactive power compensation and voltage support.
Reactive power compensation. Now that's a new one.
Yeah, it's a bit of a mouthful, but it's an important concept.
Okay, break it down for me.
So you see there are two types of power flowing in the grid.
Okay.
Active power and reactive power.
All right, what's the difference?
Active power is the power that actually does useful work,
Okay,
like running your appliances.
got it.
Reactive power is more like overhead.
Overhead, okay.
It's needed to maintain the voltage and stability of the grid.
So it's like the supporting cast.
Exactly.
Okay.
Now, too much reactive power can cause problems.
Like what?
Inefficiencies, voltage fluctuations.
Ah, so we don't want too much of that.
Yeah, really.
So that's where reactive power compensation comes in.
Exactly. Microinverters with APDCs can help stabilize the grid.
By controlling the reactive power?
Yep, they can inject it or absorb it as needed.
So they're like little grid superheroes.
That's a great way to put it.
They're not just generating clean energy.
Right.
They're actively making the grid better.
Exactly. And as we get more and more solar power on the grid,
Yeah.
these grid supportive capabilities become even more important.
It's all connected.
It is.
I'm seeing the bigger picture now.
It's amazing how these little devices can have such a big impact.
It really is. These active power decoupling circuits sound like a game changer.
They have the potential to be.
It's exciting to see how microinverters are evolving.
It is.
They're not just about maximizing solar power.
Right.
They're becoming active participants in a smarter, more sustainable energy ecosystem.
I couldn't agree more. It's a really exciting time to be following this field.
Absolutely. But for now,
Yeah.
I think it's time for us to take a little break.
Okay.
Let our listeners digest all this incredible information.
Sounds good.
We'll be back soon to continue our deep dive into the world of microinverters.
Looking forward to it.
See you then.